Our universe contains families of 7 stars bound together by gravity. This is not science fiction, but a rare and staggering reality. While twin star systems are common, a septuple star system is a cosmic anomaly so complex it defies our basic laws of physics. By the end of this journey, you will understand 25 strange discoveries that rewrite the rules of how stars live and die. How can 7 suns share one stable home without tearing each other apart? What bizarre skies would greet a potential planet in such a place? What does the existence of these stellar monsters tell us about the chaos of creation itself? What do you think happens when gravity writes a story with 7 main characters? The first and most fundamental discovery is simply that they exist at all. This fact alone is a profound puzzle. Gravity is a meticulous architect, but also a ruthless simplifier. In the vast majority of cases, complex multi-star systems are unstable. Over millions of years, the intricate gravitational dances between 3, 4, or 5 stars tend to end in catastrophe. One star is violently ejected, sent flying into the void, while others may merge or fall into tighter, simpler orbits. The mathematics of celestial mechanics suggests that a system of 7 massive bodies should be a fleeting accident, a configuration that tears itself apart in a cosmic blink of an eye. Yet we have found them. They are not accidents. They are stable, or at least stable enough to have persisted for millions, perhaps billions of years. This longevity is the first great mystery. It implies there are hidden rules, a delicate cosmic balance we are only beginning to understand. The pioneer that shattered our expectations is a star known as Nu Scorpii, or by its ancient name Jabba, the forehead of the scorpion. Nestled in the constellation Scorpius, it appears to the naked eye as a single, unremarkable point of light. But when astronomers trained their most powerful tools on it, a staggering truth unfolded. Through the precise art of spectroscopy, which splits starlight to reveal the fingerprints of individual stars, and interferometry, which combines light from multiple telescopes to achieve incredible resolution, they peeled back the layers. They did not find 2 stars or even 3, they found 7. The initial reaction was one of profound disbelief. The data was checked and rechecked because such a configuration was thought to be theoretically impossible outside of computer simulations. The discovery of Nu Scorpii was not just about adding a new entry to a catalog. It was a direct challenge. It forced astronomers to go back to their models of how stars are born, particularly within the dense, crowded nurseries known as stellar clusters. Perhaps in these frenzied environments, entire groups of sibling stars could be born so close together that their mutual gravity could, against all odds, lock them into a long-term truce. The existence of one septuple system meant our universe was capable of far more intricate and delicate architectures than we had ever dared to presume. The second strange discovery reveals the secret to their stability. These 7 suns are not engaged in a wild, chaotic brawl. Instead, they are arranged with meticulous, almost unnerving precision in what astronomers call a hierarchical system. Think of it as a set of cosmic matryoshka dolls, or an intricate clockwork where smaller gears turn inside larger ones. At the smallest scale, you find 2 stars locked in a tight, furious dance, orbiting a shared center of gravity in a matter of days or weeks. This binary pair is then gravitationally bound to a 3rd star, orbiting at a greater distance over months or years. That entire trio becomes a single unit, which then begins a slow, stately orbit around another stellar pair or group. This creates orbits within orbits, a nested gravitational architecture that prevents the entire system from collapsing into violence. Nu Scorpii, our 7-star pioneer, is a perfect example of this celestial choreography. Its configuration is often described as a pair of triple star systems, with one additional 7th star acting as a distant anchor. So you have one tight trio of stars and another tight trio of stars, and these two triples slowly orbit each other over a vast distance. Meanwhile, that seventh star orbits the entire complex from an even greater remove. It is a masterpiece of gravitational engineering where proximity and distance are carefully balanced. The close pairs are so tightly bound they act as single, heavier objects, simplifying the gravitational math for the wider system. This hierarchy is the reason the Septuple system can exist for eons without tearing itself apart. It is not a free-for-all of 7 equal bodies, but a structured, multi-layered dance where every star knows its place in an unimaginably complex routine. This hierarchical dance leads directly to the third strange discovery, a revelation about their improbable birth. We must now ask, how does a cloud of gas and dust decide to build a family of 7 suns instead of just one? The answer lies in a process of cosmic fragmentation pushed to its absolute limit. Picture the stellar nursery, a vast, cold, and turbulent nebula. As gravity begins to pull the gas inward, the cloud does not simply collapse into a single point. It spins, it churns, and it can break apart like a droplet of water splitting in mid-air. Under the right conditions, this fragmentation can happen again and again, creating multiple dense cores that will each ignite into a star. For a septuple system to form, this process must occur with an almost impossible level of precision. Take the system known as Aer Cassiopeiae. Astronomers studying its complex structure propose a startling theory. It may have begun as an attempt to build an octuple system, a family of 8 stars. The original gas cloud possessed just enough mass, spin, and internal turbulence to fragment into 8 separate seeds. But in the chaotic construction phase, something went wrong, or perhaps something went exactly right to prevent total disaster. One of those 8 stellar embryos might have been gravitationally ejected, flung out into interstellar space by its siblings in a violent game of cosmic pinball. Alternatively, that 8th core may have simply failed to gather enough material to ever truly ignite, remaining a dark, substellar object forever bound to the family but not shining as a true star. The result is the septuple system we see today, a 7-star family born from what was nearly an 8-star system. Computer simulations of this process reveal how fine-tuned these conditions must be. The initial cloud needs a very specific amount of angular momentum or spin. Too little, and it collapses into a single massive star or a simple binary. Too much, and it tears itself completely apart, scattering stars far and wide. The internal turbulence of the gas must be just right to create multiple fragments without causing them to violently merge. It is a cosmic balancing act of extraordinary delicacy. The existence of systems like Aer Cassiopeiae suggests our universe occasionally runs an experiment in maximal stellar family planning, pushing the laws of physics to see just how many stars it can pack into one gravitational sentence before the sentence collapses into nonsense. The 4th discovery introduces a jarring family portrait, one of extreme cosmic inequality. Within the same septuple system, you can find stars that are practically different species living under one roof. Picture a household containing a newborn infant, a teenager, a middle-aged adult, and a frail elder, all bound by the same set of rules. That is the stellar reality within these systems. It is possible for a searingly hot, monstrous O-type blue giant, a star dozens of times more massive than our Sun and burning its nuclear fuel with reckless fury, to be gravitationally shackled to a collection of diminutive, cool K-type or M-type red dwarfs. These smaller stars are the frugal misers of the galaxy, sipping their hydrogen fuel so slowly they could shine for trillions of years. This creates a staggering mass disparity. The most massive star in the system might contain 99% of the total mass of its immediate orbital group, while its tiny siblings are little more than gravitational afterthoughts. This imbalance is not a bug but a direct feature of their chaotic birth. In that fragmented cloud, some cores simply got more of the raw material, ballooning into behemoths while their siblings starved. The implications of this family dynamic are profound and violent. That massive blue giant is living on borrowed time. It will exhaust its nuclear fuel in just a few million years, a cosmic blink compared to the multi-trillion-year lifespans of its dwarf companions. Its fate is to die not with a whimper but with a cataclysmic bang, exploding as a supernova. This is where the story takes a dark turn. When that primary star dies, it will violently eject most of its mass into space. In an instant, the gravitational anchor of the entire subsystem vanishes. The intricate balance of forces that has held the dance together for eons is shattered. The sudden loss of mass is like cutting several strings on a finely tuned instrument. The music turns to discord. The surviving stars, now feeling a drastically weaker pull, might be flung into new, wildly eccentric orbits. Some could be ejected entirely, becoming runaway stars cast adrift in the galaxy. But the most bizarre possibility is what gets left behind. The supernova's core will collapse. If it is massive enough, it will not become a white dwarf, but will crush itself into an ultra-dense neutron star or, in the most extreme cases, a black hole. This stellar corpse, possessing immense gravity but almost no visible light, would remain bound to its living siblings. Imagine the scene. A family of small, dim red dwarfs continues its ancient orbit, not around a brilliant sun, but around the dark, gravitational pit left by their departed brother, a silent monument to the violence that once reshaped their home. The system survives, but it is forever haunted, transformed from a nest of stars into a celestial graveyard with a dark heart. This delicate hierarchy is the only reason a seven-star system does not instantly become a physics problem from hell. The classical three-body problem, which asks how three stars move under mutual gravity, has no general, stable solution. Their motions are fundamentally chaotic, meaning even the tiniest change in starting conditions leads to wildly different outcomes over time. Predicting their long-term fate is impossible. Now multiply that chaos by more than double. A pure seven-body problem, with all stars exerting equal influence on each other, is not just unstable, it is unfathomable. Such a system would dissolve into stellar carnage within a few thousand years, a mere instant on the cosmic clock. So how do we see them? The answer lies in that nested structure, which transforms an impossible seven-body problem into a series of manageable two-body problems. Each tight binary pair is so close that they effectively act as a single, heavier object. That pair then orbits with a third star, again creating a stable unit. This simplification continues up the chain, turning chaos into clockwork. But here is the fifth strange discovery, and it is a humbling one. Orbital modeling reveals these systems do not exist in a broad, comfortable zone of stability. They are perched on a razor's edge. They occupy vanishingly narrow sweet spots in a vast parameter space of possible masses, distances, and orbital speeds. A tiny nudge, a slight shift in the initial spin of the parent cloud, and the entire architecture collapses. If any of the inner orbits were just a few % wider, the gravitational influence from the outer stars would become too strong, perturbing the delicate inner dances until stars are flung away. If the masses were distributed slightly differently, the hierarchy would break down. We are not looking at robust, common structures. We are witnessing cosmic miracles of balance, rarities so fine-tuned that their very existence feels like catching a glimpse of a universe experimenting with its own limits. We are lucky to observe them at all because the window of opportunity is so incredibly small. They represent a fleeting moment of perfect gravitational harmony in a cosmos that usually prefers simpler, more violent arrangements. Their persistence is a testament not to the strength of gravity, but to its capacity for intricate, fragile beauty. The light from a septuple star system tells a story of pure chaos. When we point our telescopes at a single point of light like New Scorpii, we are not collecting the steady glow of one sun, but the combined churning output of 7. As these stars whirl around each other in their hierarchical dance, they constantly eclipse and pass in front of one another from our distant vantage point. Each eclipse causes a tiny, precise dip in the total brightness we see, a flicker in the cosmic signal. For a simple binary star, this creates a predictable, repeating pattern of dimming like a steady heartbeat. But for a system of 7 stars, the result is the 6th strange discovery, a light curve that defies all prediction, a scribbled mess of dips and peaks that looks less like a heartbeat and more like a seismograph reading during an earthquake. Untangling this signal is one of the greatest observational challenges in astronomy. It requires decades of meticulous photometry, the precise measurement of starlight, just to identify a few of the countless overlapping cycles. In a system like AR Cassiopeia, astronomers have documented multiple sets of eclipses. One pair of stars might eclipse every 3 days, creating a sharp, frequent dip. Another, wider pair might eclipse every year, adding a slower, broader wobble to the signal. Meanwhile, the other stars in the system are continuously changing their relative positions, subtly brightening and dimming the background light against which these eclipses occur. The final pattern is a maddening, beautiful cryptographic puzzle. The orbital periods revealed by this painstaking work are a study in extremes. The innermost binary stars might complete a furious orbit in a matter of days, whipping around each other at incredible speeds. The outermost members of the family, however, move with glacial patience. Their orbital journeys around the common center of gravity can take not decades but thousands of years, longer than all of recorded human history. Mapping just a single one of these long-period orbits requires comparing observations separated by generations, a testament to the patient, cumulative nature of science. This unpredictable flickering is more than just an observational headache. It is a direct signature of the system's staggering complexity, a live broadcast of 7 suns writing their own indecipherable laws across the sky. The unpredictable flicker of their light holds another, deeper secret. The 7th strange discovery comes not from their dance, but from their very substance, revealing a family mystery written in elemental fingerprints. When astronomers perform spectroscopy on the individual stars of a septuple system, they expect to find a perfect match. These are siblings born from the same swirling cloud of primordial gas and dust. They should share the same chemical recipe, the same abundance of heavier elements like iron, silicon, and carbon, forged in ancient stellar explosions long before this system was born. Yet the data tells a different story. Some stars show a distinct chemical signature, a higher or lower metallicity compared to their closest relatives. This is as baffling as finding twins with completely different DNA. Where did this discrepancy come from? One compelling theory points to planets, or rather, the ghosts of planets that never were. In the frenzied early days of the system, vast disks of gas and dust would have swirled around each young star, the raw material for building worlds. But in such a gravitationally chaotic environment, planet formation is a hazardous endeavor. The constant gravitational tugs from 6 other suns would have stirred these protoplanetary disks into turmoil, likely preventing the orderly coalescence of material into large, stable planets. Instead, this precious heavy element-rich dust and rock might have been siphoned away unevenly. One star's disk could have been robbed by its siblings, its planetary building blocks accreted onto another star, subtly enriching that star's outer layers with extra metals. Another star might have successfully formed rocky planets, locking those heavy elements away in orbiting bodies and thus appearing more pristine, more chemically poor by comparison. The system itself, in its violent youth, acted as a cosmic thief, redistributing the material for worlds before they could even fully form. Another possibility is even more direct. In the tightest binary pairs, stellar winds and magnetic fields can create bridges of superheated plasma between the stars. If one star is more massive and evolves faster, it may begin to puff off its outer layers. Its companion, caught in the intimate dance, can siphon off this material, literally stealing the enriched surface gases from its sibling. This process, called mass transfer, would directly alter the chemical makeup of the receiving star, painting it with elements processed in its partner's core. The chemical imbalances we see today are therefore forensic evidence. They are the lasting scars from a tumultuous childhood, a time when these 7 suns were not just neighbors, but active participants in a gravitational fray that reshaped their very composition. The mystery of the missing planetary material suggests that in a septuple system, the concept of a stable, quiet planetary nursery is a fantasy. The childhood of these stars was a continuous, interactive storm. The chemical scars on these stars point to a violent past, one that makes the 8th discovery all the more astonishing. We must now ask, could planets possibly exist in such gravitational madness? The idea of a world with 7 suns is the stuff of science fiction, a sky filled with a constant, shifting ballet of light. Yet, the reality of finding one is a puzzle of staggering difficulty. The primary obstacle is not the number of stars, but their gravitational reach. For a planet to have a stable, long-term orbit, it must reside in a region dominated by the gravity of just one star, or at most a very tight binary pair. This safe zone, known as a Hill sphere, is shockingly small when 6 other massive bodies are constantly pulling and tugging from nearby. Any planet venturing beyond this narrow gravitational embrace would quickly have its path perturbed, likely being ejected from the system entirely or sent crashing into a star. Theoretical models paint a clear picture. If a planet exists in a septuple system, it is almost certainly a close orbiting prisoner, hugging its host star in a frantic, short-year orbit, while the other 6 suns gleam ominously in its sky as distant, brilliant points of light. The search for such worlds has yielded only whispers and tantalizing hints. In other complex systems, like the quadruple star system Kepler-64, astronomers have confirmed a planet orbiting a pair of stars that are themselves orbited by a second distant pair. This discovery proved planets could form in incredibly complex environments, but it also highlighted the rarity. For a septuple system, no confirmed planet has yet been found. However, there are candidates, faint, periodic dips in starlight that cannot be fully explained by the complex eclipses of the stars themselves. These signals are buried in the chaotic light curves, requiring astronomers to subtract the known dance of the 7 suns to see if any tiny, repeating shadow remains. It is detective work of the highest order, sifting cosmic noise for the signature of a single, silent world. Imagine, though, the view from the surface of such a hypothetical planet. Your primary sun might be a brilliant blue giant flooding the landscape with harsh, ultraviolet light. During your short day, you might see 2 or 3 other suns hanging in the sky, each a different color, one a fierce white, another a dull orange dwarf. As the years pass, these other suns would slowly change their positions, sometimes setting in multi-star sunsets of impossible complexity, other times clustering together to cast multiple, faint shadows from every rock and tree. The concept of night might be a rare event, occurring only when all other suns are below the horizon, a brief period of relative darkness in a sky forever washed with the glow of alien suns. The very possibility of such a world forces us to reconsider the resilience of planetary formation. It suggests that even in the most chaotic of stellar families, the basic ingredients for worlds can still, against all odds, come together. Finding one would be more than just adding another exoplanet to the catalogue. It would be a monument to tenacity, a testament that life, in its quest for a home, might find a way even under 7 suns. The potential for planetary chaos hints at an even more intimate and violent reality within these star families. The 9th discovery exposes evidence of stellar collisions and mass transfer, events where the dance becomes a dangerous embrace. In the tightest binary pairs of a septuple system, stars can orbit so close that their gravitational spheres of influence merge. They enter a phase called Roche-Lobe overflow, named after the French astronomer who defined the limits of a star's gravitational domain. Picture two stars waltzing so tightly that the outer layers of the larger, puffier star are no longer bound to it alone. The immense gravity of its smaller, denser companion begins to siphon off this stellar material, pulling a stream of superheated gas across the space between them. This creates a bridge of plasma, a literal river of star stuff flowing from one body to another. In a relatively quiet binary, this process can already create exotic stellar objects. One classic result is a blue straggler. In a cluster of old stars, you expect all members to have a similar advanced age. But sometimes you spot a star that is glaringly blue, hot, and youthful looking amidst the redder elders. This star is a blue straggler, and it is not actually young. It is an old star that has been artificially rejuvenated. It stole hydrogen-rich fuel from its companion, dumping it onto its own core and effectively hitting the reset button on its nuclear fusion, making it burn hotter and bluer again. In more extreme cases, if the receiving star is a dense white dwarf, the transferred hydrogen can pile up on its surface until it ignites in a runaway thermonuclear explosion. This creates a cataclysmic variable star, a system that undergoes repeated brilliant outbursts. Now, place this intensely intimate drama inside a septuple system. The gravitational tides from the other 5 stars constantly tug on this close binary pair. They can subtly alter the shape of those Roche-lobes, squeezing or stretching them. This outside influence can turn the steady trickle of mass transfer into a sudden, violent gush, or trigger the merger of the 2 stars entirely. Imagine 2 stars already locked in a fiery dance, being periodically shoved by the gravitational hands of their distant siblings. This makes these transfer events or collisions far more unpredictable and violent than they would be in isolation. The evidence for this is written in the star's spectra and their erratic brightness. Astronomers might detect the chemical signature of carbon or oxygen processed in one star's core now present on the surface of its companion, a clear sign of stellar cannibalism. They might observe unpredictable flaring and X-ray emissions that signal chaotic accretion streams, twisted and amplified by the external tides of the family. A septuple system, therefore, is not just a collection of independent suns. It is an interactive network where a crisis in one stellar marriage can be instigated or intensified by the constant, watchful gravity of the entire extended family. The death of one star in a septuple system is not an isolated event. It is a declaration of war on gravity itself. This is the 10th strange discovery, a theoretical nightmare where one stellar death can trigger another, creating a chain reaction of cosmic violence. Consider the fate of the most massive star in one of those tight inner binaries. After millions of years, it exhausts its fuel and its core collapses. The resulting supernova is an explosion of almost unimaginable power, but in a septuple system, the blast is only the beginning of the chaos. The explosion is almost never perfectly symmetrical. As the dying star's core recoils, it can receive a tremendous kick, launching the resulting neutron star or black hole remnant at speeds of hundreds of kilometers per second. In a simple, empty region of space, that corpse would just fly away. But here, it is shackled by gravity to at least 6 other stars. That kick is not just a farewell, it is a violent shove delivered to the entire gravitational architecture. The sudden, asymmetric loss of mass combined with this kick delivers a profound gravitational shockwave through the system. Orbits that have been stable for eons are instantly destabilized. Stars are yanked into new, wildly elliptical paths. Some may be flung out into interstellar space as runaway stars. Others might be thrown directly toward each other. This is where the chain reaction begins. Picture a companion star that has, for millions of years, been peacefully orbiting this now dead giant. Perhaps it has even been siphoning material from it, becoming bloated with extra hydrogen fuel. The supernova suddenly removes the gravitational anchor holding that companion in its precise orbit. At the same moment, if the two stars are thrown into a closer encounter by the chaotic recoil, the conditions become perfect for a second catastrophe. The companion, now destabilized and overburdened with stolen fuel, could have its own core pushed over the edge. The influx of material or the sudden gravitational compression might induce its own collapse, leading to another supernova. Astronomers call this induced collapse, and in the dense, interactive environment of a septuple system, it is a terrifying plausibility. We could witness not just one, but a series of stellar explosions separated by only a few thousand or even 100 years, a cosmic string of firecrackers ignited by a single match. The system would be utterly transformed, not by the slow march of time, but by a few moments of apocalyptic fury. The surviving stars would whirl through a battlefield littered with the remnants of their siblings, their orbits forever scarred by the echoes of those blasts. This potential for a supernova domino effect makes a septuple system not just a family of stars, but a ticking time bomb with multiple triggers, where one death sentence can be passed tragically to the next. These violent possibilities make their very survival seem miraculous, which leads to the 11th strange discovery. Most known septuple systems are not ancient relics, they are galactic time capsules, remarkably young and found in the stellar nurseries where they were born. The system Nu Scorpii, for instance, is a member of the Scorpius-Centaurus Association, a nearby stream of young stars still drifting away from their birthplace. These stars are often just a few million years old, mere infants compared to our middle-aged 4.5 billion-year-old sun. This youth is their greatest scientific gift. They are snapshots frozen in the earliest chapters of their lives. When astronomers look at a solitary star like our sun, they see the end result of a long, solitary evolution, with most clues about its birth erased by time. But a septuple system is different. Its intricate orbital dance is a preserved record of the chaotic collapse that created it. Every orbital period, every eccentricity, every tilt between the orbits is a direct fossil of the initial conditions within that primordial cloud. By measuring these orbits with extreme precision, astronomers can essentially rewind the clock. They can run computer simulations backwards, testing theories of how a single cloud of gas fragments into 7 distinct cores. Did it break apart in one dramatic shattering event or through a series of sequential splits? The specific angles between the orbits can tell them. If the stars all orbit in roughly the same plane, it suggests the parent cloud was a flattened disk that broke apart like a spinning pizza dough tearing into pieces. If the orbits are wildly misaligned, it points to a more turbulent, three-dimensional fragmentation within a churning cloud. This makes a septuple system a living laboratory, a controlled experiment written in gravity and light. The processes at work here, the gravitational instabilities, the accretion of material, the dynamic interactions, are the same processes that shaped all star formation billions of years ago in the early universe. By studying these 7 sun families, we are not just looking at a cosmic oddity. We are getting a front-row seat to the fundamental, violent, and beautiful act of creation itself, watching the universe build its most complex stellar families in real time. The existence of 7 star systems forces a radical question. If the universe can build a family of 7, why stop there? Discovery 12 takes us to the very edge of possibility, into the search for even higher multiplicities. The hunt is now on for octuple and nonuple star systems, families of 8 or 9 suns bound together. This is not just a numbers game, it is a quest to find the absolute upper limit of gravitational architecture. The current record holder in this extreme category is a tantalizing, complex system centered on the star HD 98800. observations reveal it is not a single star, but a minimum of 4 stars arranged in 2 tight pairs with strong evidence for at least 2, and possibly 3, additional faint companions. This could add up to a system of 6 or 7 stars, but the data is not yet definitive enough to claim a confirmed septuple, let alone an octuple. It exists in a frustrating gray zone, highlighting the immense observational challenge. The problem is one of sheer scale and proximity. Imagine trying to distinguish 2 fireflies orbiting each other from a distance of thousands of miles, while 6 other brighter lights are blinding you from the same spot. Our telescopes, even the most advanced interferometers, have a fundamental resolution limit. If 2 stars are too close together, their light merges into a single, unresolved blob. If a companion is too faint and orbits too close to a brilliant primary star, its signal is completely washed out in the glare. We are, in a very real sense, peering through a keyhole at a distant, intricate machine, trying to count its moving parts while most of them are hidden in shadow. Yet, the very existence of stable septuple systems like New Scorpii sends a powerful theoretical message. It strongly suggests that stars are not born as lonely individuals, but often in litters. In the densest cores of stellar nurseries, the initial fragmentation of a gas cloud could readily produce 8, 9, or even 10 stellar seeds, but survival is a different matter. The gravitational landscape for a newborn 8-star system would be exponentially more chaotic and fragile than for a 7-star one. The slightest instability, the tiniest nudge from a passing cloud fragment, would likely trigger a rapid series of ejections. The system would violently simplify itself, expelling stars until it reached a more stable configuration, perhaps a septuple or more likely, a sextuple or quintuple system. The septuples we see, then, may not be the starting point. They could be the robust survivors, the gravitational last stands of even larger families that have already shed their weakest members. Finding a true, stable octuple would be like discovering a castle built on a foundation of sand that has somehow defied the ocean for eons. It would redefine our understanding of stability itself. For now, the search continues in the noisy data and the faint, flickering signals. Each unexplained wiggle in a light curve a potential whisper from an 8-star family, a ghost of a more crowded birth waiting to be confirmed. The blended light of 7 stars creates a spectral fingerprint of pure confusion. This is the 13th strange discovery, where the very colors of these stars hide secrets in plain sight. Spectroscopy, the art of splitting starlight into a rainbow to read its chemical barcode, becomes a detective story of immense complexity here. Each star contributes its own set of dark absorption lines and bright emission lines, all overlaid and smeared together by their different motions. Astronomers are not looking at 7 clean, distinct spectra, but at a single tangled mess of lines that shift and blur as the stars whirl around each other. Untangling this requires monumental patience and computational power, a process of digitally subtracting one hypothetical star's signature after another to see what remains. And what remains is often the most fascinating part. After accounting for all 7 known stars, unexplained lines often linger in the data. These are spectral ghosts, emission or absorption features that do not match any normal stellar atmosphere. They appear and disappear, shift unpredictably, or glow with the wrong color. They are the signatures of the space between the stars, a hidden ecosystem powered by the system's ferocious energy. One leading suspect is magnetically confined plasma. In the tight gravitational embrace of a close binary pair, the star's powerful magnetic fields can become tangled and snap like cosmic rubber bands, heating the trapped gas between them to millions of degrees. This creates fleeting, ultra-hot coronae that emit X-rays and produce strange emission lines not seen in solitary stars. Another clue points to violent collisions of stellar winds. Every star emits a torrent of charged particles, a continuous gale blowing into space. In a simple system, this wind expands freely. but in a septuple system, these gales from multiple stars constantly slam into each other. Where they collide, they create shock fronts of superheated gas that glow with their own distinctive, shifting spectral signatures. The most tantalizing possibility is the ghost of a protoplanetary disk. While full planets may struggle to form, vast rings of dust and debris likely still swirl around individual stars. This debris, heated by starlight and pummeled by stellar winds, can emit a faint, cool infrared glow and produce subtle spectral lines of silicate dust and molecular gas. Each unexplained line is therefore a clue to a different piece of the system's hidden anatomy. They reveal not just the stars themselves, but the frenetic, high-energy environment they have built together, a web of magnetic fury and colliding winds that turns the space between these 7 suns into a laboratory for the most extreme physics. Buried within the gravitational equations of these systems is a hidden engine of long-term chaos. The 14th discovery exposes a phenomenon called the Kozai-Lidov mechanism, and in a septuple star system, it operates on a terrifying scale. In its simplest form, imagine a tight binary star pair being orbited by a distant third star. The gravity of that distant perturber does not just pull on the binary, it engages in a slow, cosmic conversation with it. Over thousands of years, it forces a periodic trade. The inner binary's orbit can be pumped from nearly circular to wildly elongated, becoming a stretched-out ellipse, while the tilt of its orbital plane relative to the perturber swings back and forth in a precise counter-rhythm. It is a gravitational pump trading roundness for tilt and back again. In a normal triple-star system, this mechanism can create dramatic changes, but it is often limited. In a septuple system with its multiple layers of hierarchy, the Kozai-Lidov mechanism is unleashed. It is no longer a single conversation, but a cacophony of overlapping dialogues. A tight inner binary is not just perturbed by one outer star, but by several, each at different distances and angles. Furthermore, each level of the hierarchy can experience its own version of the effect. The orbit of one triple system around another can itself be pumped and tilted by the gravity of the 7th, outermost star. The result is a gravitational resonance of staggering complexity. Orbits that seem stable for centuries can suddenly, predictably yet alarmingly, begin to stretch and warp over millennia. A star in a relatively safe, circular path can be driven into a wildly eccentric orbit that brings it perilously close to its partner at regular, long-term intervals. This provides a powerful explanation for the strange chemical signatures and potential collision scars we see. A past episode of extreme eccentricity, driven by this mechanism, could have forced 2 stars into a grazing encounter or a full merger, mixing their material and leaving behind the chemical anomalies we detect today. More chillingly, it allows astronomers to peer into the future. By modeling these overlapping Kozai-Lidov cycles, they can identify which pairs in the system are on a collision course, not tomorrow, but in 100,000 years. It reveals that the serene dance we observe today is just a single frame in a movie of perpetual gravitational reconfiguration, where the architecture of the entire family is forever being subtly rewritten by forces that operate on timescales longer than human history. The system is never truly at rest, it is merely between convulsions. The gravitational tides and spectral ghosts of a septuple system are not confined to its own family. The 15th discovery reveals these stellar monsters are cosmic sculptors, reshaping their entire birth neighborhood with brute force. To understand their full impact, we must pull back the camera far beyond the intricate dance of 7 suns. We must view them within the stellar nursery where they were born, often a sprawling open cluster or a dense nebula. Here, their combined power becomes truly apocalyptic. If the system contains even 1 or 2 massive O or B-type stars, which many do, they are ultraviolet furnaces. A single such star emits enough high-energy radiation to ionize hydrogen for light years around, stripping electrons from atoms and causing the gas to glow. Now multiply that by several massive stars, all pouring their fury into the surrounding space. The result is a colossal, overlapping series of ionization fronts. These fronts act like cosmic snowplows, pushing the surrounding gas and dust into intricate, often beautiful structures. They can carve out vast cavities, creating shimmering bubbles of glowing plasma. Where denser knots of gas resist the onslaught, they are left behind as towering, dark pillars, the very kind famously seen in the Eagle Nebula's pillars of creation. A septuple system, therefore, can be the hidden architect behind some of the most iconic nebulous landscapes in our galaxy, a factory for celestial art operating on a scale of light years. But their influence is not merely radiative, it is gravitational and dynamic. Within their native star cluster, a septuple system is the ultimate heavyweight. Its combined mass, often concentrated in a relatively small volume, makes it a gravitational anchor and a potent source of chaos. As it moves through the cluster, its intense gravity acts like a ship's wake, perturbing the orbits of every other star it passes. This constant gravitational stirring prevents the cluster from settling into a calm, relaxed state. Astronomers call this virial heating or dynamical heating. The septuple system injects energy into the cluster's motions, keeping it puffed up and delaying its eventual gravitational collapse or dissolution. More dramatically, it can play a deadly game of stellar pinball. A close gravitational encounter between a single, lower mass star and the septuple behemoth can be catastrophic for the smaller star. Through a complex gravitational slingshot, the smaller star can be accelerated to incredible speeds, hundreds of kilometers per second, and ejected completely from the cluster. It becomes a runaway star or even a hypervelocity star, shot out into the galactic halo like a bullet from a cosmic rifle. The septuple system, having imparted that tremendous energy, recoils slightly in the opposite direction, further stirring the cluster pot. Over millions of years, a system like this can be responsible for ejecting multiple siblings from their shared birthplace, scattering them across the galaxy while it remains at the heart of the chaos. Its legacy is thus written in two ways: in the glowing, sculpted nebulae that bear the scars of its radiation, and in the lonely, high-speed trajectories of the stars it has exiled. The neighborhood never forgets the day a family of 7 sons moved in. This ephemeral chaos of their youth points to a deeper, more sobering truth. The 16th strange discovery is a glaring absence, a cosmic silence that speaks volumes. We do not find ancient septuple systems drifting quietly in the galactic field, far from their birthplaces. The few we have identified, like new Scorpii, are almost universally young, mere cosmic toddlers at just a few million or perhaps a few 100 million years old. Their confinement to stellar nurseries is not a coincidence, it is a countdown. These intricate families are not built to last. They are transient spectacles, a fleeting phase of maximal complexity destined for simplification by the relentless laws of gravity. Over timescales of billions of years, the quiet, persistent perturbations we discussed, the Kozai-Lidov cycles, the gravitational nudges from close passes, accumulate like interest on a cosmic debt. A star in an outer orbit receives one tiny kick from an inner pair's dance. A million years later, another. Over eons, these microscopic nudges add up to a macroscopic shove. Eventually, the delicate energy balance that keeps a star bound to the family is broken. The least gravitationally bound member, often one of the wider outer stars, reaches escape velocity. In a moment that is silent and dark from our perspective, it is flung free, sailing into the interstellar void as a runaway star, leaving its 6 siblings behind. Alternatively, the instability can drive stars inward, not outward. A gravitational resonance might shrink an orbit over millennia until 2 stars pass so close they cannot escape. They may engage in a prolonged, messy merger, combining into a single, more massive star, or they might experience a catastrophic collision, a titanic release of energy that further disrupts the survivors. Either way, the system simplifies. A septuple becomes a sextuple. Given another few 100 million years, that sextuple might eject or merge another member, becoming a quintuple. The process continues, a slow gravitational erosion whittling down the family size until it reaches a more stable, long-term configuration, perhaps a tight triple or a pair of binaries. What we are witnessing when we look at a young septuple system, then, is not a permanent feature of the galaxy. We are catching a masterpiece of gravitational architecture in the brief moment after its creation, before time and tide begin to dismantle it. Their rarity among the galaxy's ancient stellar population is the proof. They are cosmic fireworks, brilliant, complex, and utterly temporary. Their existence today is a gift to astronomers, a chance to study a level of stellar organization that the universe rarely sustains, a complexity destined to fade into simpler, quieter rhythms. The bewildering physics of a septuple star system is mirrored perfectly in the chaos of its name. Discovery 17 takes us into the human struggle to catalog this celestial madness, where our simple alphabetical systems break down completely. For centuries, astronomers have used orderly naming conventions. The Bayer designation, for instance, assigns Greek letters like alpha, beta, and gamma to the brightest stars in a constellation, usually in order of brightness. The Flamsteed system uses numbers. Both work beautifully for single, isolated points of light, but point a telescope at what you thought was one star and find 7, and the entire system collapses into hilarious, necessary confusion. How do you label 7 distinct suns when your alphabet only has 24 letters? The answer is a descent into a suffix rabbit hole that looks more like a complex algebraic formula than a star's name. Astronomers resort to a hierarchical lettering system that maps directly onto the gravitational architecture. The primary component of the system gets the original designation, say Nu Scorpii. The star closest to it in a tight orbit becomes Nu Scorpii A. Its even tighter companion becomes Nu Scorpii R. If that primary star has another, more distant companion, that becomes Nu Scorpii B. That star's own close partner becomes Nu Scorpii Bar, and so on. You end up with a cosmic family tree written in letters, Nu Scorpii R, Ab B, Ca CB, and so forth. The designation for a specific star in such a system can look like a secret code. HD 163296AB Ca, for instance. This isn't bureaucratic pedantry, it is a precise linguistic map. The suffix string R tells you immediately that this star is the primary member of the innermost binary pair within subsystem A. It is a direct translation of the gravitational hierarchy into text. To look at the official name of a star in a septuple system is to see a schematic of its orbital relationships. This naming chaos underscores a profound truth. Our language and cataloging methods evolved for a simpler, quieter cosmos. They are overwhelmed by the reality of these complex families, forcing us to invent new, more intricate linguistic tools just to keep track of the pieces. The name itself becomes a testament to the staggering complexity it represents, a reminder that the universe's architecture often outpaces our attempts to neatly file it away. The naming chaos of these systems is a prelude to a far more violent future symphony. The 18th discovery lies not in the light they emit, but in the silent ripples they will one day send through the fabric of space itself. When the massive stars in a septuple system reach the end of their lives, they do not simply vanish. Their cores collapse into the universe's most extreme objects, ultra-dense neutron stars or bottomless black holes. And in the ultra-close binary pairs that form the backbone of these hierarchical families, a new and terrifying dance begins. Imagine 2 city-sized neutron stars, each weighing more than our entire sun, locked in an orbit so tight they could fit between the Earth and the Moon. They are the corpses of sibling stars, forever bound by the gravity that once held them as living suns. As they whirl around each other at a significant fraction of the speed of light, they do something extraordinary. They radiate energy not as light, but as gravitational waves, invisible ripples in the very geometry of space-time, predicted by Einstein over a century ago. Each orbit loses a tiny amount of energy to these waves, causing the stars to spiral inward, imperceptibly at first, then with gathering, inevitable speed. Over millions of years, the orbit shrinks from years to days to seconds. The final moments are a crescendo of distortion. The two remnants merge in a cataclysm that shakes the cosmos, releasing in a fraction of a second more power than all the stars in the observable universe combined. This merger sends a final, thunderous blast of gravitational waves echoing across billions of light years. Observatories like LIGO and Virgo on Earth are now listening for these signals, and they have heard many. But here is where a septuple system becomes a factory. We are not talking about a single, tragic merger. The architecture of a septuple means it could host multiple such close binary pairs, each on its own collision course. Furthermore, the gravitational tides from the other stars in the system can actively shepherd these stellar corpses together, tightening their orbits faster than they would in isolation. Over the next billions of years, a single septuple system could sequentially produce not one, but several of these universe-shaking mergers. It becomes a gravitational wave assembly line. The first pair of black holes merges. The resulting, more massive black hole then continues its dance, perhaps eventually merging with another black hole left behind by a different sibling. The system, born in a frenzy of light and plasma, would thus transform into a dark engine of space-time tremors, its history written not in photons but in the warping of the universe's foundation. To detect a gravitational wave signal and trace its origin back to a known septuple star system would be a monumental discovery. It would connect the visible, complex architecture we see today with the invisible, violent destiny that awaits it, proving that these stellar families are not just cosmic curiosities, but the birthplaces of the deepest ripples in reality. The gravitational stability of these 7 star families may depend on a celestial trick borrowed from our own solar system. The 19th discovery introduces the Trojan star hypothesis, a theoretical idea that adds another layer of delicate architecture to the already complex hierarchy. In our solar system, the giant planet Jupiter shares its orbit with thousands of asteroids, not randomly scattered but clustered at 2 specific points in space. These are the Lagrange points, positions where the gravitational pulls of the Sun and Jupiter perfectly balance with an object's orbital motion, creating zones of stability. The most famous are the L4 and L5 points, located 60 degrees ahead of and behind Jupiter in its orbit. Here, the asteroids, known as Trojans, can orbit the Sun in a stable, synchronized dance with the planet for billions of years. Now, transplant this concept into the frenzied environment of a septuple star system. Within one of its wide binary pairs, astronomers theorize that a third star could be occupying one of these Lagrange points, acting as a co-orbital companion. This would not be a simple third star in a wider orbit, but a star literally sharing the same orbital path as its partner, leading or trailing it by 60 degrees in a perpetual gravitational lockstep. In such a configuration, the 3 stars, the primary, the secondary, and the Trojan, would form an equilateral triangle that rotates gracefully around the system's center of mass. This Trojan arrangement provides a profoundly stable niche. It prevents the co-orbital star from drifting into a dangerous, perturbing path that could scatter other members of the family. It is a built-in gravitational harmony within an already intricate dance. For a septuple system, this could be the hidden glue that stabilizes one entire level of its hierarchy. Imagine a subsystem where 2 stars orbit each other at a moderate distance, and each of those stars has its own close binary companion that already makes 4 stars. Now add a 5th star as a Trojan, co-orbiting with one of the wider pair. This creates a stable pentagon of gravitational forces, a configuration far more robust against external tugs from the other two stars in the full Septuple system. While no confirmed stellar Trojan has been definitively observed in a Septuple system yet, the mathematics are compelling. The same physics that herds asteroids around Jupiter could very well be shepherding entire suns in these extreme families. Finding one would be a triumph of celestial mechanics, revealing that the universe uses the same elegant solutions, Lagrange points, to stabilize everything from tiny rocks to massive, shining stars. It suggests that within the apparent chaos of seven suns, there exists an order so precise it relies on the same gravitational sweet spots that have guided spacecraft across our solar system. The potential for Trojan stars transforms our view of these systems from mere hierarchical stacks into interconnected geometric puzzles, where stability is found not just in distance but in perfect, synchronized alignment. The dust that might have formed planets does not simply vanish. The 20th discovery peers into the wreckage of that process, observing the faint, warm glow of debris disks stubbornly clinging to their stars. When infrared telescopes like Spitzer and the James Webb Space Telescope stare at a Septuple system, they are not just looking for light, they are sensing heat, the thermal signature of countless microscopic dust grains warmed by the stars they orbit. In simpler systems, this infrared excess is a clear sign of a circumstellar disk, a flat, rotating ring of leftover material where planets could be coalescing. But in the gravitational storm of a Septuple system, detecting this faint heat is like hearing a whisper in a hurricane, and its very existence is a profound puzzle. The environment here is merciless. Intense ultraviolet radiation from the massive stars constantly bombards these dust grains, pushing on them with physical force in a process called radiation pressure. This alone should blow the finest dust out of the system entirely, like a cosmic leaf blower clearing a driveway. More destructive still are the relentless gravitational tides. As the seven stars perform their complex dance, their combined gravity does not pull in one steady direction. It tugs and kneads the disk material from multiple angles at once, creating immense shearing forces. A disk that tries to form a neat, flat plane around one star will be violently warped, twisted, and likely torn apart by the passing gravitational influence of its six stellar siblings. So, what do we actually see when we find this infrared excess? We are not looking at pristine, planet-forming nurseries. We are looking at the survivors of a cosmic demolition derby, the shattered remains of what might have been planetary building blocks. The structure of these debris disks would be unlike anything in our solar system. They would be pockmarked with vast gaps, cleared by the gravitational resonances of passing stars. They would be warped into three-dimensional shapes, not flat rings, looking more like crumpled pieces of paper than dinner plates. Some material might even be trapped in stable, but bizarre, locations like the Lagrange points between stellar pairs, forming dusty clouds that lead or trail a star in its orbit. These distorted disks are not just curiosities, they are forensic records. The specific pattern of gaps and warps encodes a history of past gravitational encounters. By modeling the disk structure, astronomers could, in theory, work backwards to trace the orbital evolution of the stars themselves over the last few million years. Furthermore, the mere presence of any dust at all suggests a continuous grinding process. Small asteroid-like bodies, called planetesimals, must still be colliding with each other in this chaotic zone, perpetually replenishing the dust that radiation is constantly trying to erase. This means that despite the hostility, the basic ingredients for rocky worlds are still there, still colliding and trying to build. It is a testament to both the violence and the tenacity of the cosmos. Even under seven suns, the universe is still trying and failing and trying again to make something solid from the chaos. Beyond gravity and radiation, a hidden force weaves through the stellar nursery. Discovery 21 reveals the subtle but critical role of magnetic fields in binding a Septuple system together. Young stars are not just balls of hot gas, they are colossal dynamos spinning rapidly and generating magnetic fields millions of times stronger than Earth's. These fields extend far out into space, forming vast, invisible magnetospheres. In the crowded, violent womb of a forming septuple system, these magnetospheres do not exist in isolation. They collide, merge, and tangle. Picture 7 powerful magnets being swirled together in a cosmic fluid. Their invisible lines of force inevitably snag on one another. This creates magnetic bridges, temporary or semi-permanent tunnels of twisted magnetic flux that connect the infant stars. These bridges are not just curiosities, they are active participants in the system's survival. During the system's most turbulent infancy, when gravitational forces were at their most chaotic, these magnetic connections acted as a cosmic shock absorber. They transferred something crucial: angular momentum. Imagine 2 spinning ice skaters clasping hands. As they pull together, their individual spins change, slowing one down and speeding the other up, but their combined rotation finds a new shared balance. Magnetic bridges between nascent stars can perform a similar feat on a stellar scale. They can siphon off excess spin from a star that is rotating too fast, preventing it from tearing itself apart, and transfer that energy to another or dissipate it into the surrounding cloud. This process helps shepherd the wild, individual motions of the 7 newborn stars into a more synchronized, collective rhythm that gravity can then lock into its hierarchical dance. Observations in star-forming regions like the Orion Nebula provide strong clues. There, astronomers have mapped the magnetic fields threading through protoplanetary disks, seeing how they guide the flow of material onto the growing star. In the far more extreme case of a septuple birth, these fields would not just guide gas, they would directly link the stars themselves. They could channel material along their lines, yes, but more importantly, they could provide a stabilizing tension, a subtle web of force that helps counteract the random gravitational kicks that would otherwise doom the complex configuration. While gravity is the grand architect drawing the blueprints, magnetism may have been the skilled craftsman on the construction site, quietly ensuring the pieces fit together tightly enough to last. This magnetic glue is likely a fleeting phenomenon, most powerful in the system's first few 100,000 years before the stars drift to safer distances and their fields weaken. But that brief, magnetic embrace during the most volatile phase might have been the decisive factor that allowed a potential octuple to become a stable septuple, or that prevented a nascent sextuple from flying apart entirely. It is a reminder that to understand the universe's most elaborate structures, we must look beyond the most obvious forces and listen for the silent, pervasive hum of magnetism shaping chaos into form. The magnetic embrace that may have shaped their birth points to a deeper conceptual problem. These 7 star families do not just challenge physics, they challenge our very language for describing the cosmos. Discovery 22 forces a philosophical question, one with no easy answer. What, in the end, even is a star system? Our textbooks draw neat distinctions. A binary star system is 2 stars orbiting a common center of gravity. An open cluster is a loose group of hundreds or thousands of stars, born together but only weakly bound, destined to drift apart over time. A septuple system exists in the bewildering gray zone between these categories, a cosmic hybrid that defies our desire for clean classification. Is it one system, or is it a miniature, temporary cluster? The answer depends entirely on which pair of stars you are looking at. Consider the outermost member of a family like Nu Scorpii. It orbits the central complex of 6 stars, but that orbit may take 10,000 years or more. The gravitational tether is incredibly faint. From the perspective of that distant star, the inner 6 are just a single, bright point of light. Is that star truly a member of a septuple system, or is it merely a very long-period companion to a massive sextuple star? The bond is so tenuous that a close pass from another star in the galaxy could sever it completely. Conversely, the innermost binary, with stars whipping around each other in a matter of days, is welded together by gravity of unimaginable strength. They are a single, inseparable unit, so within one named object on our star charts, we have the entire spectrum of gravitational relationships, from the matrimonial to the barely acquainted. This continuum reveals a profound truth about nature. It does not care for our human-made categories. It does not decide, here I will make a binary, and there I will make a cluster. Instead, it simply obeys the laws of physics in a cloud of collapsing gas, and the result is a glorious, messy spectrum of possibilities. A septuple system is a snapshot of that spectrum, a single gravitational sentence containing every possible clause from a tight conjunction to a distant, dangling modifier. Their existence tells us that the universe operates in gradients, not in boxes. What we call a star system is not a fundamental category of nature, but a convenient label we slap on a particular level of gravitational complexity that happens to catch our eye. By blurring this line so spectacularly, these 7 sun families humble us. They remind us that our maps are always simplifications, and that the true cosmic reality is far more interconnected, fluid, and wondrously untidy than any catalog can ever capture. The blurred line between a single system and a miniature cluster leads to a staggering, almost science-fictional possibility. Discovery 23 proposes using these 7 star families not just as objects of study, but as tools, transforming them into the universe's most powerful telescopes. The principle is rooted in Einstein's theory of general relativity, which tells us that mass warps the fabric of space. A massive object like a galaxy or a star acts like a lens in this warped space, bending the light from objects behind it. This phenomenon, called gravitational lensing, is already a cornerstone of modern astronomy, allowing us to see galaxies otherwise too faint or distant to detect. Now imagine the lens is not a single galaxy but a septuple star system. Its total mass, concentrated in a relatively small volume of space, creates an intense, complex warp. If by a 1 in a billion cosmic alignment, a distant quasar or galaxy were to pass directly behind such a system from our viewpoint, its light would not simply bend. It would shatter. Instead of producing a single magnified image or a neat Einstein ring, the light would be twisted and split by the 7 separate gravitational wells. The result would be a kaleidoscope of multiple, distorted images of the same background object, arranged in a bizarre pattern dictated by the precise positions and masses of all 7 stars. This would be lensing chaos, but a chaos rich with information. For astronomers, catching such an event would be like winning the cosmic lottery. By meticulously analyzing the exact arrangement, brightness, and distortion of each fractured image, they could perform a feat of reverse engineering. They could map the gravitational field of the entire septuple system with a precision impossible by any other means. It would reveal the exact mass of each star, even the dim, hidden ones we struggle to see directly. It could expose the presence of dark matter subtly clinging to the family, or confirm if any of the components are not stars at all, but black holes by the unique way they warp the light. Furthermore, this natural 7-star lens would provide an unparalleled window to the early universe. The magnification power would be immense, allowing us to study the structure of that background galaxy in exquisite detail, seeing features otherwise forever beyond our reach. The challenge, of course, is the staggering improbability. The alignment must be perfect, and the event would be transient, lasting only as long as the background source stays in the precise line of sight. It requires constant, wide-field monitoring of the sky, waiting for the rare moment when a septuple system's gravity becomes a lens. Yet, the mere possibility reframes these stellar families. They are not just in points of curiosity, but potential instruments, cosmic artifacts that might one day, by chance, become our most powerful lenses for gazing into the deepest reaches of space and time. This cosmic lensing reveals a truth beyond pure physics. These stellar families also shape the stories we tell. The 24th discovery finds them not just in telescopes, but in the ancient myths of our own planet, and in the profound cultural shifts they would force upon any world born in their light. Long before astronomers decoded its seven-star nature, Nu Scorpii held a place in human sky lore. Known as Jabba, it marked the forehead or back of the scorpion in the constellation Scorpius, a celestial beast woven into stories from Greek mythology to indigenous Australian Dreamtime. Our ancestors saw patterns and projected narratives onto those fixed points of light, never suspecting that a single point could be a teeming stellar metropolis. This human impulse to find meaning in the stars takes on a staggering new dimension if we consider a hypothetical civilization evolving on a planet within a septuple system. Their entire existence would be framed by a sky of overwhelming complexity. Our simple rhythm of day and night, summer and winter, dictated by one sun and one moon, would be utterly foreign to them. Their concept of time would be a layered puzzle. They might track not one primary year, but multiple overlapping celestial cycles, the furious 3-day orbit of their closest sun, the slower 30-year dance of a binary pair, and the millennia-long procession of the outermost sibling stars across their heavens. Calendars would be mathematical masterpieces, and the idea of a day might not exist at all, replaced by periods of varying brightness as different suns rose and set in a never-repeating sequence. Their mythology and religion would be fundamentally shaped by this perpetual celestial ballet. Where we might have a single sun god, they could have a pantheon of 7 deities, each representing a star with a different color, temperament, and orbital rhythm. Their myths might explain the rare, terrifying event of a total eclipse by one star as a temporary victory of a dark god, or the clustering of 3 suns in the sky as a sacred time of alignment and power. The very idea of cosmic order would be different. Our astronomy developed from observing predictable, clockwork motions. Theirs would be born from observing a dynamic, chaotic-seeming system that nonetheless possesses a deep, hidden stability. A stability they might attribute to the delicate balance of divine wills rather than to gravitational hierarchy. Their art, their poetry, their very sense of place in the cosmos would be filtered through the experience of living under multiple suns. A quiet, starry night as we know it might be the stuff of their most ancient legends, a lost golden age when the gods slept. This thought experiment does more than ignite the imagination. It underscores a profound scientific point. Our understanding of the universe is inextricably linked to our singular, two-body perspective. The discovery of septuple systems violently expands the palette of possible cosmic experiences, reminding us that the laws of physics can paint realities far stranger than any myth we have yet invented. Our stories, it turns out, were only ever about one possible sky. This final, strange discovery forces us to look billions of years into the future to witness the end of the dance. Every intricate hierarchy, every delicate balance is temporary. The ultimate fate of a septuple star system boils down to 2 stark possibilities, each a different flavor of cosmic simplification. The first is a quiet dissolution, a gravitational evaporation. Over timescales that dwarf the age of our solar system, the persistent tugs from close encounters within the cluster and the internal Kozai-Lidov cycles will do their slow, inevitable work. One by one, the stars with the weakest gravitational bonds, typically the outermost members, will be nudged past their escape velocity. They will drift away, their light fading into the galactic background as runaway stars. The septuple becomes a sextuple, then a quintuple, then perhaps a stable quadruple or a tight triple. The process is not explosive, but a whisper, a gradual forgetting of the original, sprawling family. The system fades into a simpler, more common configuration, its extraordinary past erased by the relentless tide of time and perturbation. The second possibility is far more dramatic, a final act of violent consolidation. Here, the very mechanisms that define the system become its executioners. Consider a close binary pair, its orbit gradually pumped to extreme eccentricity by the quasi cycles driven by its outer siblings. On each close pass, the stars nearly graze each other, their atmospheres touching. Tidal forces drain orbital energy, and over thousands of such perilous encounters, the pair spirals inward. They do not separate, they merge. The collision of two suns is a cataclysm of almost incomprehensible energy. It does not typically cause a supernova, but it does create a single, bloated, rapidly spinning stellar monster, a blue straggler on a colossal scale, its outer layers heated and churned by the titanic impact. This new, more massive star becomes an even stronger gravitational player. Its increased mass can destabilize the orbits of other pairs in the hierarchy, potentially triggering another merger cascade. Like falling dominoes, the intricate clockwork could collapse into a single, furious event. In the most extreme scenario, if the merging stars are both massive enough, or if the final merged product is unstable, the end result could be something even darker. The system might forge an intermediate mass black hole, an object hundreds or thousands of times the mass of our Sun. This dark remnant would then sit at the heart of what was once a brilliant family of 7, its gravity still perhaps holding a few ejected, traumatized stars in distant, mournful orbits. All visible evidence of the septuple origin would be gone, consumed in a final, brilliant flash of light and a silent, gravitational sigh. So, what we observe today is a snapshot of magnificent but fragile order. These systems are caught between the chaos of their birth and the inevitable simplicity of their death, whether that death comes as a slow fade or a spectacular fire. They are cosmic experiments in complexity, and every experiment, no matter how beautiful, must one day reach its end. The universe builds its most intricate palaces not from stone, but from spinning, burning suns, and it seems content to watch them both shine and crumble under the weight of their own impossible design. These 25 discoveries paint a portrait of a cosmos far more intricate and daring than we ever supposed. A septuple star system is not merely a celestial oddity, it is a full-scale physics laboratory operating at the extremes. Every facet of its existence, from its improbable birth in a fragmenting cloud to its potential death as a gravitational wave factory, challenges the clean models in our textbooks. These families force us to rewrite the rules of gravitational stability, to reconsider the chaotic processes of star formation, and to witness stellar evolution not as a solitary process, but as an interactive, often violent family drama. Their very rarity is what makes them cosmic treasures. They are the universe's experiments in maximal complexity, fleeting masterpieces of balance that show us just how far the laws of physics can be stretched before they snap. So the next time you gaze up at the night sky, at what seems like a sea of solitary, twinkling points, remember the hidden truth. Some of those points are not single stars at all, but teeming metropolises of light, where 7 suns are locked in a dance of unimaginable grace and violence, a dance that has rewritten our understanding of the heavens. Which of these strange discoveries captivated you the most? Was it the potential for planets under 7 suns, the gravitational time bomb of a supernova chain reaction, or the haunting idea of stellar Trojan points? Share your thoughts in the comments below, and if you want to journey deeper into the universe's most bewildering mysteries, be sure to subscribe.